Numerical number 5. Students will take one more numerical number 5. Afterwards, we'll take one more numerical, that is numerical number 6. In this numerical, basically, you will be finding the velocity gradient. In fact, very simple, you have to find dv by dx. So you have to find the relative velocity between the two layers and divided by the distance of separation between those two layers, of which you are calculating the velocity gradient, relative velocity. So the question is, the relative velocity between two layers of liquid separated by 0.1 mm. The relative velocity between So relative velocity between two layers separated by 0.1 mm is this. Calculate the velocity gradient. Nothing to solve much in this part. You can take any two layers. The distance of separation between these two layers is given as 0.1 mm is your dx from any origin. If I consider this as x1, this as x2, then this dx is x2 minus x1, which is your dx, which is 0.1 mm. The velocity of the relative velocity between the layers is 2 centimeter per second. That means if I consider this as velocity, this layer is moving with the velocity v1 and this is moving with the velocity v2, then what is given is v2 minus v1 equals to dv equals to 2 centimeter per second. So you can assume that this is 0 or this is 2 centimeter per second. That also means 2 centimeter per second is the relative velocity, or you can take this 1 centimeter per second and 1 centimeter per second. You can take this as 1 centimeter per second and this as 3 centimeter per second. Then also it is 2 centimeter per second. So this can be any value, but then you add 2 to this. So this basically v2 is nothing but 2 plus v1. So that is how you get the relative velocity. So what you will get, the dv by dx you put, then you will get the answer like dv by dx is 2 divided by 0.1 mm is there, so divided by 110, so 10 here, so it is 200 is the answer. Students, will take one more numerical, that is number 5. It is this numerical is based on that Stokes law that we derived. The viscous force acting in a freely falling sphere is 6 pi times eta rv, that is the viscous force. Now the question is, if let me write the question. Find the viscous force acting on a raindrop The question is, find the viscous force acting on a raindrop. Okay, we have to find the viscous force acting on a raindrop which is falling, whose diameter is 2 mm, falling through a with a velocity. This is velocity is a constant velocity, so this is a constant velocity. The coefficient of viscosity is given as 1.8 × 10⁻⁵ per unit in SI system. So viscous force solution. The viscous force is 6 pi eta rv. Okay, 6 pi eta rv. So you can put the value directly, nothing is given much. 6 into pi is 3.14, eta is 1.8 × 10⁻⁵. R is here is the diameter is 2 mm, so radius is 1 mm. So 1 mm is how much meter? That is 10⁻³ meter. So this is 10⁻³ into velocity is 2, So just put this value, plug this value and get the answer. So you multiply these numbers, and I'll just write for you. This number comes out to be 0.678 10 raised to minus 6 Newton. This is a very small viscous force that is acting, but whatever it is, this is the viscous force when a raindrop falls and attains a terminal velocity of 2 meter per second. That time its weight and the buoyancy and the upward force, these two will together will balance this. And the viscous force part, out of these two, one is viscous force, another is the buoyancy force. The viscous force is this much Newton. Okay, thank you.